MarkLogic 12 Early Access 1 introduces really the first iteration on our vector search roadmap. The capabilities in EA1 allow extraction and storing of vector embeddings in the database and calculation of vector similarity distances, allowing for implementation of techniques such as re-ranking of search results based on vector similarity. We will build on this by adding approximate nearest neighbor indexing capabilities in the final release of MarkLogic 12. These vector operations can be combined with our existing search techniques such as structured metadata queries, full text queries, graph, geospatial, all to be able to implement the most flexible, multi-model, hybrid RAG techniques available. Before I jump into a demo of this, I need to talk a little bit about the Optic API. Optic API is key to understanding how vector operations can be combined with other multi-model queries in MarkLogic. MarkLogic Optic API is really our flagship query language for running multi-model queries in MarkLogic. The Optic API allows you to combine CTS queries, SQL queries, Sparkle queries, geospatial queries, and now vector similarity queries in MarkLogic 12. The Optic API has data accessors, joins, aggregations, and declarative updates that are all composable into a pipeline of operations. Also key to using vector operations in MarkLogic is the template-driven extraction feature. In MarkLogic, you can use a template to specify how you want data to be projected out of documents into different views and graphs. You can project rows or graph data or graphs in the form of triples from JSON or XML documents. You can cast the values that you project out of the documents using a rich language for selecting the data and casting those values into primitive or complex data types, such as geospatial or in MarkLogic 12 vectors. The Optic API is developer friendly. It's meant to be usable from really all of the areas where you would write code to interact with MarkLogic, whether that's server-side JavaScript, an XQuery, a domain-specific language for Optic API, through the REST API, via the Java client, Node client, and also through our Python client. So with that, I'm going to jump in and show you a demo of what it looks like to work with vectors in MarkLogic 12 Early Access 1. Once again, I'm going to be using MarkLogic's Query Console to really look under the covers at what's going on with our vector operations in MarkLogic 12. For this demonstration, I'm using some wiki data that has been collected and has been run through an embedding algorithm to generate embeddings for each of the wiki entries. These are just summaries of wiki entries, so they're small chunks of text. With this, I'm going to show you what the documents look like. In this database, we have a total of about 300,000 documents. Each of the documents looks something like this. We have an ID, we have a title, we have some text, we have the original URL, and then we have a vector embedding that was calculated for the text within this document. So using this data, I'm going to go through a scenario that it shows how to combine our traditional MarkLogic multi-model searches with vector re-ranking. In order to get the embedding out of the document and into the vector storage in MarkLogic Server, we need to use a TDE template, as I just described. A TDE template can be represented in XML or in JSON, and it describes how we want to select the data to project into rows or triples. In this case, the vector index is integrated with our row index. And so we need to create a new view called wiki vectors. And within that view, we're going to have a number of columns. We'll have an ID column, a title. We'll even extract the text out into a column. We'll pull a URL. And then the most interesting one, the new thing, the new capability is the vector. So in MarkLogic 12, we have a new scalar type within TDE called vector. And we have a new function called vector, which allows you to construct vectors from a node that you have extracted from a document. So if you have a JSON document with an array of numbers, you just pass that array into the vector function, and that will extract that vector and add it to the vector storage within the MarkLogic storage and indexing engine. You also need to specify how many dimensions that vector is, and note that all of the vectors within a given column need to have the same number of dimensions, otherwise it doesn't work correctly. So with that, let's jump into a scenario. For simplicity, for the demonstration, I've taken a question and I've already run it through an embedding, so I don't have to keep running it. And I've generated a question, and that question is, what species of birds don't fly? I ran it through an embedding model, and I generated a vector for that question, and I stored that in the database as well. Obviously, in a normal query execution, you wouldn't be necessarily storing that in the database, just doing this for the sake of demonstration. If we were to take this simple query of what species of birds don't fly, we could do a naive approach and just break that query into its words, right? This is English, so I'm just going to split on spaces and generate the words of that are in that query. I can run a lexical query that finds all of the documents that have those words in them. So let's talk a little bit about what is going on here. So in this query, I'm getting the text, or I'm starting with the text rather, of what species of birds don't fly. I'm going to use a naive approach to split that text into the words, and I'm going to generate a standard CTS query for those words, right? So any of you who are MarkLogic users would be familiar with the CTS query language. I'm going to do an AND query of a collection. This is the wiki data collection. And I'm going to do a word query on the words that were in that text. And that's just what you would call an OR query, or a shotgun OR query of all of those words. Additionally, I'm going to specify some query options. In this case, I'm going to specify the score method of BM25. So this is the new BM25 scoring algorithm, as I talked about before. If you didn't want to use BM25, you could use this the default TF-IDF, or you could even use score 0 if you didn't want to take that relevant score into account. And the length weight is the new parameter that allows you to specify the weight of how much the document length impacts that score, right? So a higher weight means that documents that are shorter would be boosted in score. In this case, I'm just going to set it at 0.5. Because most of these documents are approximately the same length, so the length weight is not really impacting this use case that drastically. In this example, I'm generating an optic query, This is an example of an object query that does a search. I do from search, and I specify the document query and the options that I want. I order by the score. So this is the standard score generated from a CTS query. I only want the top 10 of those. And then I'm going to select a few fields out of the document to return as the results. I'm also just because I'm interested, I want to know the total number of documents that match my document query that I've specified here. So if I run this, I see there's actually about 200,000 documents match my query, which is not surprising because I think, you know, the word, there are some quite common words in there like of and what. But as we know with like TF-IDF, those documents should be lower on the list from a stop word perspective. So let's take a quick look at some of the examples. I see I have right at the top, I have a document that talks about birds. And I even have as a second document here, one that talks about flightless birds. I have some, this is one that talks about hawks. Those are definitely not flightless. Grebes are flightless. I guess elephant birds are flightless. Anyway, so if we go down, we can see down also at the bottom in this top 10, we have some documents that are not really about birds at all, but they do have those keywords or some of those keywords. So right off the bat, we can see, you know, just with a lexical search, it's pretty good. Let's take a look at what we can do with vectors. Moving on, let's talk about vector search. With the vector operations in MarkLogic 12, we can do a simple scan of the vector storage to identify the documents that have the closest vector similarity to the text embedding that's generated for the question. Now, note, as I mentioned in earlier in the introduction slide about the feature, MarkLogic 12 Early Access 1 introduces the vector operations, but we're still working on the actual indexing that would allow this to be fast at scale with, you know, millions of documents. But even without an index, we can see that we can use the vectors for simple re-ranking processes, which I'll go into in more detail with the hybrid search. With the vector search, instead of starting from the search, which we did in the previous query, we can start from the view. We can start from the wiki vectors view that we created using the TDE that I showed earlier. From the view, we can create a new column called cosine similarity. That cosine similarity column, we are going to calculate a value that we put into that column using the cosine similarity function. So the cosine similarity function is going to take in two parameters. The first one being the column that contains the embedding that we've extracted from the documents, and the second argument being the query vector, the vector that we have generated that represents the query. So when we run this, we will have a new column that tells us the cosine similarity distance between the source documents in the database and the query vector that we've calculated. We're going to order this by the cosine similarity, and we're going to run the top 10. So we run this. This takes a few seconds. This is just for full disclosure, this is just running on my MacBook in a Docker container with a couple of cores. So even with those 300,000 vectors, it takes a few seconds to run it. We can see based on the vector similarity, the documents we get back are also interesting. We get some documents about butterflies. We're talking about flight, some waterfowl. Here we get one about flightless birds, more about flightless birds, things about the Barcula, which is not this, I guess apparently is not essential for flying. But also, we get we get some documents that are also, not necessarily about flightless birds, but about birds in general, right? So much like the lexical search, we get back a set of documents that sort of vary in actual relevance to the semantic intent of the question. But neither of them are perfect. So let's see if we can make them a little bit better. To do that, we're going to run what I'm calling a hybrid search. Now, yeah, keep in mind there's lots of different approaches out there for RAG, as I mentioned, and there's hybrid. RAG means a certain thing to certain people, but hybrid is a very sort of broad word that can mean a combination of different approaches, right? For RAG, in this example here, I'm going to show doing a lexical search using the query mechanism that we already went through, identifying a top candidate list of documents, and then using the vectors to re-rank those to identify a smaller top K number of documents that we could then feed into an LLM. So same setup as before. We have the query, what species birds don't fly. We have the text embedding that we've generated for it. We're going to split that into words, generate a document query for our lexical search. We're going to use BM25. I'm going to specify a few parameters here. I'm going to actually pull back the top 1,000 documents from my lexical search, because I'm really focused on recall for my lexical search, right? And then I'm going to use the vectors to re-rank those documents to identify the top 5 out of those documents. The query vector, I'm gonna construct a vector out of the text embedding that I have generated previously for that question. So now, as I said, I have a few parameters. I have I'm going to do a lexical search for the top 1,000. I'm going to re-rank using a query vector to find the top 5. And then I'm going to use a weighting factor to determine how much the cosine distance score impacts the overall the final score that gets calculated. So if I run this, actually, if I set this to 0, what this does is which should be essentially equivalent to just the lexical search. So if I run this, I see, this should look familiar. The first document I hit is the one about birds. Second one is about flightless birds. Third one's about Harrier. If I increase this though, let's bump this up to 0.5. So now I'm going to use the similarity score to impact the overall final score that gets calculated. So the idea behind this is that I would be able to take the semantic intent that's encoded into the query vector and use that to better identify which of the top 1,000 documents are the actual most relevant for my question. So if I use 0.5, I run that. Now we see actually the top 2 documents are actually, our top 3 documents are about flightless birds, right? So that's working pretty well. So we see flightless birds, grab another one about flightless birds. general one about birds, get this one about butterflies, which is interesting. Not sure why that is, but as we know, none of these algorithms are 100% precise. So this is an example of how we can combine the lexical score with the vector similarity distance to identify the most relevant documents. Let me go through in a little bit more detail what this query looks like. Like the vector query, the standalone vector query, we're going to start with the view, which is the wiki vectors. We're also going to start with the lexical search using from search. And the from search, we're going to limit it to the top K. So this is the top 1,000. And we're going to order those by the score. So now we have the top 1,000 documents. We have a view that has the vectors. Using the Optic API, we can join together the document result set with the vector view, and we can join it on the document ID within those views. We can then generate a column called cosine distance, which we already discussed in the previous example. The cosine distance, which is the distance between the embedding column and the query vector. We can also then create a new column called the hybrid score column. And we can use a helper function that we've created called vector score, which uses that weighting factor and combines the lexical score with the cosine distance score to generate a combination score weighted based on the cosine distance. This is just one algorithm that we've started with. I anticipate we'll be adding more algorithms. You can also implement your own. The Optic API is fully functional, and you can add your own calculations to that as well. As before, we'll select out the data that we want to show in the results. And then finally, we're going to order by the hybrid score, and we're going to limit it to the re-ranked top K, which at the top we set that to 5, right? So with that, that wraps up the demonstration for vector operations in MarkLogic 12 Early Access 1. I hope you find that useful.